So combinations are happen when we want to take a selection of objects where the order doesn't matter. And so our formula for combinations, we're going to look like this. It's going to be NCR, is the formula for permutations, n minus r factorial, but we need to divide back out the number of times the pattern we're looking for comes through. And so what we're saying is we take all the permutations, but we divide it by how many times the things we have selected has showed up, so that we only get one for each combinations of things. So remember when I had the 3 different color balls, in a pot, and if I pulled 3 out, I would have 6 different combinations or permutations, because it was n factorial. Now, if I were to only pull 2 out of this, my options could be, I could get the pink one and the yellow one. I could get the pink one and the orange one. I could get the yellow one and the orange one. I could get the yellow one and the pink one. I could get the orange one and the yellow one. And I could get the orange one and the pink one. This actually has 6 permutations, choosing 2 of them, because there's only one option left for the ball remaining. But notice that and that are the same. And this and this are the same if order doesn't matter. In fact, if order doesn't matter, I only have three ways I can get things out. But by pulling 2 balls out, I only get 3 options. And that's what this formula helps us determine. So let's look at a particular example where order doesn't matter. And find out how many combinations we can get of something where order doesn't matter. So I'll use the example in the book. There are 16 companies bidding on 4 slots. And these 4 slots are identical. So it doesn't matter if company 1 comes first or company 2 comes first. They all end up getting the same contract. So it doesn't matter, order doesn't matter. So we'll do 16, 4. 16, choose 4. So we get 16 factorial over 16 minus 4 factorial times 4 factorial, all in the divisor here. Now we could write this, we could say, hey, there's 16 factorial upstairs with 12 factorial times 4 factorial. And we know previously that these 2 would cancel each other out, because this is 16 times everything all the way down to 1. This is 12 times everything down to 1. Well, these factors would cancel each other out, leaving me upstairs with 16 times 15 times 14 times 13. Downstairs with 4 times 3 times 2 times 1. And so 4 goes into 16 4 times. 3 goes into 15 5 times. 2 goes into 14 7 times. And so this becomes 4 times 5 times 7 times 13. Or we could go to our calculator. And we could say, hey, we have 16 things. And we're having a combination where order doesn't matter. I'm going to choose NCR, and we're choosing 4 out of those, and we get 1,820. And so there are 1,820 combinations where these 16 companies could fill these 4 bids where order doesn't matter. Now, we're going to move on and we're going to try to take these back to probabilities in the next slide. What I want to appreciate, and I would look at slide 15 in the slides, or I'd look in the book where they have the summary of the counting principles, but all of these things meant probabilities. And what we're going to use this for is for looking at a way to generate our probabilities, both for a very large number of outcomes and a very large sample space. And so we need the tools to count over these large spaces, and that's why these counting principles are important to us.